Welcome everyone, or maybe just Rui. Yeah, welcome to.
We have more people. Don't worry.
Okay,
more
great.
People have joined. You can be encouraged. Don't worry.
Okay. Yeah, welcome to how to build a full stack blockchain application. My name is Martin. I'm a senior software developer here at Partisia, and I've worked on both the development of the blockchain itself, the core blockchain, and also I've built applications on top of this blockchain. And today I'm going to talk about some of the things you should consider when you build a full stack application. At least some of the things that we consider, and we do this with two example applications here today. Application 1, which combats cyber attacks, and application 2, which is a humanitarian token solution. I will introduce the two applications, what it is they do, what problems they're trying to solve, and then I'll go through contract state separation and CK computation, so how to define the contract state and the zero knowledge computation itself. And then I will go through some general things when you build applications, which is both how you deploy and test the contract and how you communicate with the blockchain from your front end. And then I have a short slide, which just is there to provide a better understanding of secret variables in the smart contract. So the first application, which is to combat cyber attacks, is made in collaboration with the Cyber Peace Institute, where the objective is to enable non-governmental organizations to collaborate in dealing with cyber attacks. So the prerequisite is that each NGO already has a list of identified identifiers of compromise, where an identifier of compromise, IOC, is a standardized deterministic description of, exactly that, an indicator of a compromise. And I have a couple examples here of the of some indicators of the Lockbit 2.0 ransomware, where some commands are recorded in relation to this attack. These are listed on the top, so long commands through the CMD, and also files are created at these particular locations with these names. So this is just sort of a snippet of the many indicators of compromise of this Lockbit 2.0 ransomware attack. So the NGOs will have these things recorded, and what they want is to actually communicate with each other to find out which other NGOs are having these same indicators of compromise, without actually telling and broadcasting to everyone which indicators you have found. So you only want to secretly input your indicators of compromise, the ones you found, and then you want to find out who has seen these same attacks themselves, and then you can bilaterally communicate with these NGOs to say, how should we solve this problem? How should we defend ourselves against this cyber attack? So a requirement for this is that all IOCs input by an NGO should be secret, which means that each NGO should only know their own input and the match bit of the other NGOs. Yeah, so as an example, I have here 3 IOCs known by NGO 1. This is the only information that is known by the NGO 1, where a file has been created at this location with this name, they've recorded this command, and there has been communication with this IP address. These IOCs are input to the computation, which will then result in match or no match for the other NGOs. So for the file that was created, They know that both NGO 2 and 3 have found this, but none of them have found the recorded command, and only NGO 3 have had communication with the IP address. So now they can communicate between themselves and then actually talk about which IOCs they want to handle. So, for instance, the recorded command, neither NGO 2 or 3 knows that NGO 1 has found this compromise, whereas both of them now know that all of them has found this file that was created. So the first thing we do when we want to develop a smart contract that can solve this problem for us is to separate state, essentially which information can be public and what should be private. Where in this case, we want to have the blockchain addresses of the NGOs, the participating NGOs, public. This allows us to limit the access to specific invocations to the contract, meaning that we can assert that only participating NGOs are inputting IOCs to this computation. So we know exactly who will be inputting these, and we can reject any other inputs. Then we have the information that we want to keep private, which are the indicators of compromise that are registered by the NGOs, so the inputs. And we also have the match vectors for each IOC, which contains the match bit for each of the other NGOs, which is the results of this computation. One thing to note is that all secret values are stored equally as variables. It's just a list of variables on the contract, which means that IOCs and the corresponding bit vectors are stored in different variables. Some of them are inputs, some of them are results, but they just look the same. So we have to add some public metadata to these things. For each variable, we also need to know who is the owner of this variable, which NGO is behind this IOC input, or should be able to see this result match vector. And also we should know whether this variable is an IOC or a match vector. As all variables are secret, encrypted, it's not possible to see if this is an IOC or a match vector. So we need public metadata to say this is a result and this is an input. So we should add that as well. And then finally, the result variables should contain a reference to the corresponding IOC variable, so that you get, but afterwards an NGO gets a list of results, but they need to know which result is actually corresponds to which input. That information can be public as well. So there's actually a lot of public information on these private variables. Now, when we have to define the CK computation, one thing we have to keep in mind is that the protocol, the CK computation engine, it works on numeric values. So it has to be numbers. And the IOC's input here are strings. So we have to choose a conversion scheme which is known to all parties, and we have to apply this conversion before we input. So the conversion should be done client-side before we actually send anything to the blockchain and the CK nodes. In this computation, we're only performing equalities. We're just comparing, are these two IOCs the same? If they are, then they match. If they're not the same, then there's not a match. So we only want to do quality comparisons. There's no need for less than or greater than equals or something like that. It's only equality. So we can use a hash function here and then say that an input variable is a 32-bit integer. And we can then hash the IOC string and take the 32, for instance, least significant bits of the hashed IOC. So this is a way to go from the string down to an actual 32-bit numeric value that the zero knowledge computation engine will be able to compare to other values. And then we define the results of the CK computation, which is a results bit vector, which is computed for each input variable, where there is a bit for each of the NGOs, if there is a match or if there is not a match. Now, it just shows here a 32-bit integer. For choosing the size of your variables, it's not something we have to consider, but it's not a unique problem for CK smart contract development. But it is, however, much more influential when we are working in this MPC paradigm, as computations become much slower and much more expensive the larger the variables. So as we have to find a trade-off between performance and reducing the probability of a hash collision, as we're only using a substring of the hash. So for instance, if we use the I32 as before, we only use 32 bits of for instance, a 256-bit hash function, which will then increase the probability of a collision, but it is much cheaper than, say, a 64-bit number. So we have to keep this trade-off in mind. How much do we want to avoid collisions? Are we comparing billions and millions of IOCs, or are we comparing 10? How many bits do we need, and how fast do we want it to be? And then find the balance between those two. Then you have to consider actually paying for this. You're working on the public blockchain, and as using any blockchain, you have to pay fees, pay gas to use it. And you can see down here the cost of operation. The input, the 3 NGOs input their IOCs, it's relatively cheap, and then the CK computation itself is much more expensive than inputting. So the most straightforward way of programming the contract would be to wait for all parties to have input, and as soon as the last party inputs, start the computation. But that means that the last party that inputs will pay all the fees for the zero knowledge computation. This is the simplest way of programming the contract, but it does not necessarily seem that fair. So that's one way of doing it. Another alternative way of doing it is that each party inputs, but starting the CK computation is a manual process, manual action that has to be triggered by someone. It might not necessarily be the 3 NGOs. It could be a fourth party that wants to fund this. So as it is can be seen as a charitable project, some party might want to pay for the computations. Another way of doing it is to actually take some extra fees every time a party inputs. So prepay the CK computation. So the cost is shared equally, because you pay a bit more than what the input costs for every time you input. This is possible, but it's a more complex way. You have to actually program this. You have to make the code that does this, and you have to find out before the computation starts how expensive is it. So it's more complex than the first two alternatives. Then we have a fourth and final alternative, which is sort of a different approach. And the computation here can be started by any of the NGOs, but it only computes a part of the computation, the part of the computation that's relevant for them. So, for instance, if NGO1 starts the computation, only the IOCs input by NGO1 are considered when comparing to all the other IOCs. So you are not computing the entire match matrix. You're only computing the vectors for the IOCs input by NGO1. And this is a way of splitting up the fees. It might actually be the sum of all these might be larger than if just doing the computation all at once. But it's at least you only pay for your own work. It's not that relevant in this case because the results can be seen as sort of two-way. You get a result that, yeah, it's two-way result. You get a result that both you and NGO2 have this IOC. But it's something that you could consider for other computations, maybe just doing a part of the computation and then split out the cost in this way. And then just have a slide of all the four alternatives. Now, you have created your contract, you have compiled it, and the compiler outputs two files, a contract file, a WASM file, either WASM or CK WASM, and also an API. And these two files can be used at the testnet dashboard, where you will be able to upload these files and then actually simply deploy your contract to the Partisia Blockchain's testnet to see it live, to see it work. Yeah, so you can deploy the contract in there, and you can actually also interact with it. The dashboard dynamically generates all these supported actions that you have created on the contract and enables you a simple, crude way of sending actions and invocations to your contract to actually test it before actually making your own front end. This is a good way of testing it and see it working live before deploying it to the mainnet. Then we have some things to consider when we develop front ends. This is a screenshot of the front end for the Cyber Peace Institute application, where we can see the list of indicators of compromise of an NGO and whether they have found a match and who they have matched with. So in this case, NGO2 and 1. But how you should get this information is using the blockchain as a backend. So how do you actually do this? You could communicate with a reader node, where the reader node will provide the entire blockchain state to you. So you can fetch the state from that reader node, but doing this, you are now putting all your eggs in one basket. So to say, you're trusting this reader node. That might be fine and sufficient if the reader node is trustworthy, but you might also want to add multiple reader nodes that you communicate with. Maybe you can compare the states that you receive. Maybe you can switch between them. There are multiple different solutions. Of course, it's more complex than just communicating with a single reader node, but it might give, at least it will prevent this attack. An alternative, but also more complex solution is to create your own custom reader node, which will then become part of the blockchain network, and you can communicate with that as you trust that node entirely. This also gives the added benefit of actually you can put a database on this custom reader node, and you can store additional information and maybe indexing to easily provide your front end with the relevant information, because the default reader node just supplies the blockchain state, and you might want something a bit different and right more tailored to your front end. So this is a good way of doing it, but it takes, of course, more development time. So now, as with any application, this application you load it and you retrieve data, you retrieve the state from your backend, which will be the state at that point in time. And as the blockchain changes with every block, you are now reading the state of a previous block. This is not something new. If you are used to, what can we say, Web2 programming with a web server, you're not getting updates unless you actually refresh the page or you have some sort of push system set up. So as you see here, the state changes are not pushed by the blockchain. You have to fetch these. So for some applications that do not change state that often, in this case, the CPI, Cybersecurity Institute application, is one of those, I think, where a snapshot is sufficient. Then you can just refresh the page if you want to see it has something changed. But if that's not sufficient, you can poll the state. So you can ask, give me the state now with a fixed interval. What is it now? What is it now? Or you could actually have if you set up a custom reader node, you could have that server actually push down changes to your front end. But of course, it's more complex than the others, once again. But it's something we have to consider when we create these front end applications. How do we get the state from the blockchain, and how do we keep it live? And then, as I mentioned, I have this short slide about just sort of a background knowledge of the secret variables in the protocol and in the entire environment. So as an example, an IOC over here is represented by 8 bits in this case. So not a lot, but it's just enough for this example. I want to input this IOC to the nodes, but I wanted to keep it secret. So I create something called secret shares, where I actually fragment the input into 3 other bit strings, also of 8 bits. These are completely random, and from the outside perspective, they tell us nothing about the IOC itself, the input IOC. But they have this relation that if you XOR the 3 values together, then you get the input IOC. So this is the idea behind it. You have one value, you split it into 3 that individually tell nothing about the input. But if you have all of them, then you have the actual input. And then you send each a share to a CK node. So one of the computation nodes performing the actual MPC will only know one of these, so will know no information about the input IOC, but the protocols will be able to actually compute using these secret shares. So the IOC is input in this, compared using the underlying protocols, and then the results are exposed in the same way, but in the other order. So bit strings that individually tell nothing about the output is sent to the client, which will then reconstruct them, say XOR, to get the actual result. And this is just an example of one secret sharing scheme. The secret sharing scheme used on the Partisia blockchain is Shamir's secret sharing, which is based on Lagrange interpolation instead of XOR. We have development kits or libraries available that can both take an input, split it up, send it to the servers, and also get secret shares from the servers and reconstruct it. So these things have been made easy for you. So then I have the second application. I'll try to go through some of the same things and considerations that we have for the first one. This is the humanitarian token solution, which is made in collaboration with the International Committee of the Red Cross in the ICRC, where here the objective is to protect the privacy of individuals receiving monetary aid from the ICRC. And to do this, we've created sort of the idea behind it is to have a token contract, as you know from the crypto space, where the ICRC will be able to deposit money, mint, to people. So in this case, deposit 100 tokens to Alice, who will then be able to transfer 10 to Bob. So the ICRC can deposit tokens into the token contract, and then users will be able to transfer tokens to each other within this contract. This is a very, very crude way of looking at it, but it has some obvious problems. For instance, that here the names are public. You don't want, as the objective was to protect the privacy of these people, so that no one will be able to know who Alice is sending money to. So who's sending money to who? So a step in that direction is to pseudonymize everything. So instead of having Alice and Bob's names on the contract, we could have pseudonyms. So from an outside perspective, when A transfers, it transfers 10 to B. No one knows who A is and who B is. They just know that tokens have been transferred. But the problem here is now that ICRC, they need to know who they're transferring money to. They have a list of known beneficiaries that they know these people should receive humanitarian aid from us. So they need to know where to send the money. So now the ICRC, they know the identity of the pseudonyms A and B, and they will then be able to follow the activity of the beneficiaries. So what we're working with now is this diagram. It sort of has the same things as the previous slide, where to the far left we have the users, Alice and Bob, and the next column is the ICRC, and then the next two columns are the token contract. First the private part of the token contract, and then the public part of the token contract, where we have introduced a private part to ensure that the ICRC cannot follow the money and do not know who is behind these pseudonyms on the token contract. So the idea is that inside the private part of the token contract, there is an entry for each of the beneficiaries. So for instance, there is an entry for Alice, which has a secret value, a public value, and a balance, where these are probably not the best names, as these are all secret. So it's a public secret and a secret, but it's just a language we use for this application, and I hope you will be able to understand it. So in this case, the ICRC are able to deposit money into the private part of the token contract by using the public value. So I input which public value should receive how much money, and then the person who knows the secret value of an entry will be able to take the money take the amount in the balance and then move it to a chosen pseudonym. This is all going on in secret, which means that the withdrawal now becomes anonymized. So the ICRC knows they have put money into the private part of the token contract, and at some point there is money on the public part of the token contract. but they have no relation, no way of knowing the relation between these. So if you go through the state separation once again, for this application, we need to know the blockchain of the ICRC, because those that should be the only ones allowed to deposit money into the private part of the token contract. And then we also need the map of token balances for each of the pseudonyms in the system. So essentially just the public token contract. And then for the private state, we have this list of balances that are ready to be claimed by the corresponding beneficiaries. So the CK computation, we define each variable as a tuple, a secret tuple, which contains the secret value, which is known by the beneficiary, and the public value, which is known by the ICRC, and the balance value, which reflects the balance available to be claimed. So when we deposit, or when the ICRC deposits, they input the public value and an amount. So, and then this amount is added to the balance of the tuple containing the public value. So it goes through all the tuples that are on the contract, on the private part of the contract. Then it secretly adds the amount to the balance of the tuple containing the secret public value. And then from the user's perspective, when they want to withdraw, they send in the secret value and a pseudonym. So where should the tokens be sent on the public token contract? So the public token balance of the pseudonym is then increased with what was in the balance value of the tuple containing the secret value. And then the balance is set to 0. So these inputs, the ones in square brackets, are private, so those are secret. So then no one from the outside can see what was the public value, what was the amount, and what was the secret value. The only thing that's public here is the pseudonym, but it is now anonymized. So now we have created, or we have actually delinked the person that the ICC they send money to, and then the pseudonym on the token contract. So the ICC will no longer be able to follow the money or the tokens sent to a particular beneficiary. I just have the diagram once again. Yeah, thank you. That was my presentation. I don't know if there are any questions.
Guys, if you have any questions, so please do some reactions so we can know to let you talk, or you're also welcome to write questions in the Q&A section as well. Any question going once, going twice? Thank you very much, Martin.
Thank you.
We have a question. We have a question.
Oh.
Forten asking a question regarding the first application. Where should the NGO get the gas to pay for the ZK computation? From donations, no? That's how they get, or from government that gives the money.
Yeah, those are non-governmental organizations, so it should be, they should get the money of the gas on the blockchain like anyone else, I think, with the bring your own coin token bridge. So yeah, they should sort of have some BYOC on the blockchain to be able to pay for the CK computations and the inputs.
Forten, did that answer your question?
Great.
Cool. Thank you very much. Have a nice day, evening, breakfast, wherever you are.
Yeah, you too. Thank you for listening.
Ciao.
Yeah.